9, and then we're going to hopefully get into a little bit of chapter 10. Okay? We drew the Lewis dot structure for this compound here, the xenon-containing compound, which is an interesting compound because, you know, xenon is a noble gas, and noble gases generally, people just think, oh, they don't form compounds. They do form compounds, but it's only been relatively recent that we've recognized that they can form compounds and the conditions under which they can. But we drew this one. Is that not true, Alyssa? Did we finish drawing this, the Lewis dot structure for this one?
Yes, sir. I think we did.
Okay. And we also finished drawing the, well, we didn't do SbCl5. Okay. Why don't I give you a little hint on HCO3 minus, and then I'll break us into groups and we'll try to work on SbCl5 and HCO3 minus. Okay? Listen carefully because you might be the only one in your group that understands the two hints for HCO3 minus. The two hints are, one, the hydrogen does not connect to the central atom, and two, the negative charge there means that we have one additional electron in our valence electron collection. The negative sign means we have an additional electron in our valence electrons, and hydrogen does not connect to the central atom. It connects to one of the atoms, but not to the central atom, which is carbon in this case. All right, with those two clues, why don't you break up into groups and work on these two compounds here, okay? There we go. All right, there we go. Does anybody, before I break out, does anybody, well, I'll come through the groups. Hopefully everybody has the opportunity to actually draw these compounds on the whiteboard that should be available to you. Okay, here we go. Hello?
Hello? Hello?
You there?
Yeah, I'm here.
Catherine, are you there?
Yeah, I'm here.
Excellent. You guys working on it?
Yes. Do you know how to make the background just white? Is there a way, or we just work around it?
I don't know. Let's see if I think that you can do this.
I'm just trying to figure that out. Oh.
Erase yourself a spot. But no, I cannot figure out, and I've looked on YouTube and looked on different tutorials to figure that out, but I don't see that that's available to it. But this is just a big...
eraser.
Yeah.
Okay, thank you.
Okay.
All right.
Hello?
Hello?
So all the way to the side, it has 18 valence electrons, unless it's different because it's a noble gas. Okay. Well, I think that would be in the middle as the least, right?
I'm making some space for you here. Okay.
Oh, thank you. Oh, thanks.
So what you guys want to do...
Question.
Yeah, you guys, we did xenon oxygen fluoride last time, right?
Oh, I thought we were doing all
No, just do the last two. Just do the last two. We'll focus on the last two.
Okay.
You're on carbon, right?
Yes. So we have the 6 available to it, so we just need to write 2 more.
Mm-hmm.
Okay.
Wait, so right now we have 1, 2, 3, 4, 5.
The first one. I just checked back in my notes. I don't think we did.
Yeah, that's what I was saying. I don't have them either. So
Yeah, I'll tell them when we get back to the lecture.
What's that? What are you missing? Say that again.
I think we didn't actually do the first one.
Oh, you didn't do the first
I
one?
looked back in my notes.
All right, we'll do that when we get back then.
I don't think we actually did it.
Okay, we'll do that when we get back. I'm making some space here for you guys.
oh, I didn't know we could delete those.
Well, you can't really, but you can write over them in white, and then it.
Gotcha.
So I'm kind of like using an eraser here. Okay, let's see what you guys got. Go for it.
Oh, so it's probably going to be the SB.
There we go.
05.
Yeah. So you went 7 around.
What?
So when you not put 7 around, like, could you account for these 2 being 2?
Well, like they are just that. The 7 is just what they're bringing to the party. So all together, we're gonna have valence electrons that need to be accounted for. Each of the elements they want a 8. First, you gotta count on. So there's 1, 2, 3, 5 bonds. So that's gonna be 10 electrons, and you subtract 40 total. So then you have 30 accounted for. So you have left for the chlorine. So let's count.
So you wouldn't need 1, 2, 3, 4, 5, 7. You only need 5, right?
6, 1, 5. Yeah, that would be good because they'd each after the bonds are taken out, and then the 5 chlorines. We're good.
Hydroblankic model, but these acids, oxyacids, are not named following that model, so that's not correct. Ellen Noah, let's see. Well, I think this is a hard question to answer in the text box below. Emily Eddington, do you know the name of that acid there? H2SO4?
No, I don't.
Okay. Joey?
Is it sulfuric acid?
That's right, sulfuric acid. And the way, what that's helping us remember is that sulfate goes to sulfuric. Do you know the name of this acid, H3PO4, Joey?
Phosphoric acid? Something like that?
Phosphoric acid. Very good.
Phosphoric acid. Yeah.
Phosphoric acid. All right. So it's an oxyacid. H2PO4 is an ion of that acid where one of the hydrogens has been lost, right? So we could draw a chemical reaction here where H3PO4, let me get it the right color here. H3PO4 dissociates into H2PO4 and a hydrogen ion, right? Okay, so H2PO4 is an ion of an oxyacid. And all oxyacids have the hydrogens on them coming off of oxygens. So in Lewis dot structures for for oxyacids or for any ion of an oxyacid, we have to have the hydrogens coming off of the oxygens. Okay, let's draw then, or let's count up. Where are we at? Kyla, Sam, or let's see. Kyla, yeah, you can answer this in the text box below or in the chat below. How many electrons are in this molecule, this species, H2PO4 minus? How many electrons do we need to have on our molecule? Kyla Samford, you there? Oops, I got to go to public chat. There we go. 32, let's see. We got phosphorus brought 5, oxygen 6, 1, 2, 3, 4, 24, 29, 30, 31, plus the negative charge, 32. Very good. Okay, so we got 32 electrons. Then, how many electrons do we already have down there, Kylie?
Oh,
12. 1, 2, 3, 4, 5, 6, 12. So 32 minus 12, does that leave us with 20 electrons left over?
yes.
Okay. Somebody want to write that number for us there? I got it. Okay, 20 electrons. Now, where are our next electrons going to go? Who's up? Anastasia. Where's the next electrons going to go?
To oxygen.
Yeah, why don't you start distributing electrons on the oxygens?
One, two, three, 4, 5, 6.
Am I doing it to all of it?
Yeah, keep going. Brielle and Camilla, why don't you guys help? And Camille also. Okay, so we got 6, 10, 11, 12, 13, 14, 15, 16. What's going on down here? Okay, are we done? How many do we put on altogether? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay? So we're out of valence electrons. All right, formal charges, Chance. Tell me about the formal charges on these oxygens. Is everybody happy?
No.
Okay, what's wrong?
I think one of them's bringing. Oh, wait a minute. No, they're all happy.
They're all happy?
Yeah, the oxygens are happy. The phosphorus is not happy.
Okay, what's the formal charge on this oxygen here, Chance? Are you saying it's 0?
Yes.
Okay, so how many did it bring to the party?
Oh, hold on. Sorry. It bring an extra one. It's supposed to bring 6, but it brought 7.
Okay, so what is its formal charge then?
It's going to be negative.
That's right.
1.
Negative 1. Very good. Why don't you write that on there, Chance? And what about the bottom oxygen? Is it in the same scenario, Chance?
Yes.
All right. And then you said the phosphorus wasn't in a good shape. What's its condition?
It is positive 1.
Yeah, very good. Okay, it brought 5 and it only has 4 electrons right around it. So how can we fix this, Chloe?
Well, usually you like rearrange the electrons and put more like bonds, right?
Okay, right.
But for a question,
yeah,
like for this one, since it's -1, and then +1, do you like add those up? So like overall it's -1?
well, that is the case, and that's something to take into account because we do know that in the end, the sum of the formal charges should be -1. How do we know that the sum of the formal charges should be -1 in the end?
Because it's written on the top that, yeah.
Right. It has a -1 charge. So, yes, that's true. And that's something that we don't want to be afraid of, but we do want to try to make it so that our molecule, we're not done here because we want to verify that our molecule cannot get fewer formal charges. All right. So is there a way, Chloe, that we can reduce the number of formal charges that we currently have?
Yes, we just have to rearrange some stuff, but.
All right. What do we have to rearrange?
I'm not sure yet.
Okay, so look at, for example, the +1 and the -1 here. What does the -1 mean? Do you remember, Chloe?
It's like electronegative or something.
It has excess electron density. And the
Okay.
+1?
It's the opposite of that.
It's what? It's what?
It doesn't have enough.
That's right. It doesn't have enough electron density. Very good. So, what
Can you
are
put
we-
one,
Yeah, go ahead.
like one of the pairs of electrons on the oxygen, like you can change it to be between the phosphorus and oxygen?
That's right. That's right. So go ahead and why don't you do that?
Right there. And then I don't know how to erase.
You just choose white instead of red over to the right.
Okay.
But I can do that for you, actually. I'll just erase those ones there. Okay, good. So that ends up with no formal charge there. Does that also fix that? Yeah, it fixes that. If you choose a little bit larger circle, then it erases a little bit better. Got it. Okay, excellent. So, Chloe, can we do that again?
Yeah, you could do it right here again.
All right. So, if we did that again, we would lose our -1 charge here. And then would we be done? Daisy, what do you think?
It just added a positive charge to the phosphorus, isn't it?
Positive? Count it up again. Make sure.
Well, because the phosphorus brought 5 to the party, right?
It
And
brought.
that gives it.
That's right.
But now the formal charge would be 6. So then wouldn't that make it a +1?
5 minus how many?
You're right. I always forget which one is on top and bottom. So that gives it a negative charge.
All right.
-1.
So it has a -1 charge. So essentially what we did, that first one helped things out because this oxygen didn't have a formal charge and the phosphorus didn't have a formal charge either. But when we brought that second one in, we just traded the location of the -1 formal charge from oxygen to phosphorus. Okay, hopefully everybody can see that. So the question is, what's better? Is it better to have a negative charge on the phosphorus or a negative charge on the oxygen? Eleanor, do you have any ideas? Do you want to type in down below? What's better, to have a negative charge on the phosphorus or the oxygen? Any thoughts based on that? And remember that negative charge means electron density. Emily, do you have any ideas? What do you think? Which one would be preferred to where to have that negative charge? Ephraim, any ideas? Any preferences on where you? Oh, Emily, are you there? Go ahead. Where do you think it would like to have the negative charge?
I guess I'm not like totally sure, but would you want it on the oxygen? Because
Would you want like the main element to be negative?
Okay. So I don't know about what it means to be the main element, but the one that is more electronegative would like to have more electron density. Would that make sense?
Okay, so then wouldn't you want it on the oxygen?
That's right. That's right. So we would like to have that negative charge. Right now it's on the phosphorus, right? And we don't have it necessarily written right now, but it's easy to write. I'll write it there. So right now it's -1 charge is there, but it would be better if it's on the oxygen because the oxygen is more electronegative. So Emily, can you write it on the oxygen, and can you rearrange also the electrons so that they are showing a negative charge on the oxygen? How do we want to rearrange those electrons, Emily?
Would you have to take some? Would I just put them on the top?
Okay, so you would remove it from a bond, right, and form them into non-bonding electrons, right?
Yeah.
All right. Good.
And then remove these.
That's right. Remove those. Okay, very good. And now we have to make sure we write in our negative formal charge that we have on our oxygen. -1 there. Okay. Now, as far as oxyacids go, this compound, right, which is H2PO4, we can imagine this compound coming in contact with a hydrogen ion, positive charge, right, and forming H3PO4, okay, and based on our Lewis dot structure, H3PO4, based on our Lewis dot structure, we can tell where that positive charge would like to end up, right? The positive charge is going to be attracted to where the negative charge is, and the bond is going to form right there. Okay, very good. So, hopefully we're feeling more comfortable drawing these Lewis dot structures. We're going to, I think we're getting it. We're going to talk about a few more concepts and then finish up here. One concept that we want to be aware of is that when bonds form, molecular bonds, covalent bonds, usually we think of them as one element bringing an electron and another element bringing an electron, and then the sharing occurring, right? So hydrogen, hydrogen, both bringing an electron, right? Let me see here. Gotta focus that camera a little bit. Okay, hydrogen, hydrogen coming together. In the end, we have a hydrogen-hydrogen bond between those two. Well, sometimes it happens that there's such thing as what's called a coordinate covalent bond, which means that one element brings all the electrons to form the bond. One element brings all the electrons to form the bond. And the scenario that's given up here in this example is something like NH3 coming in and interacting with H plus to form NH4 plus. And in this case, H plus is forming a bond with the NH3, but H plus doesn't have any electrons of its own. So you have, let's draw this out, NH3, if we do all the electrons and everything, we find out that there's a lone pair of electrons there. Okay, and then we add H plus, and these electrons right here reach out and grab onto that H plus and result in another bond being formed. All right, the resulting compound has a positive charge, but this bonding here is not a sharing of electron density initially. It's not, I mean, it ends up being a sharing, but the hydrogen didn't have any electrons to share in the first place. And bonds can form this way as well, where electrons come from just one location. And the resulting bond, we call it a coordinated covalent bond. Okay? Now, if we look at ions, polyatomic ions, like the carbonate ion, CO3 2-, or the phosphate ion that we just drew, all right? When we're drawing these compounds, right, we draw these compounds, and we get to a point where we have finished our compound. So, for example, we had, if we were to draw the PO4 3- ion, the PO4 3-, our compound would look like this. All right. And we wouldn't think much of it. That's that. However, there is a little bit of a difference, at least in the way, in terms of the way we've drawn it, between this oxygen and that oxygen. All right? Bonds, a carbon-carbon bond, for example, compared to a carbon-carbon double bond or a carbon-carbon triple bond, right? Joey, what do you think? Which one of these would require more energy to break?
I would say the top one.
Okay. Now, remember, how about this? I have a carbon-carbon double bond, and I perform some chemistry, and now I have a carbon-carbon triple bond somehow. Would this process release or require energy?
It would release energy.
It would release energy. That's right. How did you know it would release energy?
Because they release energy when you accept more electrons.
That's right. When you form a bond, right? So when there's more bonds, that means there must be what? More
Less energy?
More
More
energy.
energy.
There's more energy stored in those bonds, right?
Mm-hmm.
The system is more stable. And it also goes as far as the energy necessary to break the bonds. So if this, well, I have the slide here at the end that talks about this. And you can see that the energy necessary to break a triple bond is more than that to break a single bond, which hopefully follows the pattern that we're understanding. Because when a bond exists, it means that there was stability found. If you can't, I mean, you can't form a bond and require energy to form a bond. That just doesn't happen, right? So when we look at this compound here, this PO4 3-, we would have to say that one of these bonds, either this oxygen-phosphorus double bond or this oxygen-phosphorus single bond, is stronger than the other one. Kyla, can you write in the chat box, which one do you think is stronger, the phosphorus-oxygen double bond or the phosphorus-oxygen single bond? The single bond, the stronger one, is actually the double bond, right? Double bonds are stronger than single bonds. So same with carbon bonds here. As you go down here, we're getting a stronger bond. Stronger bond. It requires more energy to break a triple bond than it does a single bond. So this phosphorus-oxygen double bond is stronger than this phosphorus-oxygen single bond. What about bond lengths? Kylie Johnson, Kylie. What do you think? What bond is shorter, the oxygen-phosphorus single bond or the oxygen-phosphorus double bond?
I have no idea.
Okay, let's look at this this table right here for carbon-carbon bonds. Which one do you think is going to be shorter then, a phosphorus-oxygen double bond or a phosphorus-oxygen single bond?
Double bond.
That's right. The double bond is shorter. A double bond is shorter.
What makes it shorter?
Well, there's more electron density being shared, and so the atoms are brought in a closer proximity, right? As more electron density is circling around or associating with two different nuclei, the atoms can get closer together. Now, if we look at this atom of phosphorus, sorry, not atom, but molecule, polyatomic ion, phosphorus with 4 oxygens, the phosphate ion, right? In experiments, if you try to do experiments that will tell you the length of these bonds, what you find is, on average, each one of these lengths is the same. They're not the length of a single bond, and they're not the length of a double bond. But what they actually are is they're the average length of 1 double bond and 3 single bonds. And what that tells us is that when we have a molecule like this, the electron density is traveling around. So this double bond takes turns being on one oxygen, and then it goes to another oxygen, and then it can travel to another oxygen, okay? So you have these different, what we call structures, resonance structures, where electrons are moving around the molecule. And they don't necessarily have to move in this order. They could go from here to this structure over here. So all of these structures are the same structure, but the electron density is moving all around the molecule all the time. Okay? And this results in what we call resonance structures. So if we were asked to draw 3 different resonance structures, or the different resonance structures for the nitrate ion here, you would see how the double bond could either be here on this oxygen, or over here on this oxygen, or over there on that oxygen. Okay? And what these resonance structures teach us is that, let's see, go back to this one here. What these resonance structures teach us is that the stability of the molecule can find stability if it has more regions in which the electron density can move around. So the phosphate ion, for example, PO4 3-, it finds stability in having more spaces where the electron density can move around. All right? And so the strength of this bond, of these bonds, would all be an average of the strength of all those bonds. The length of these bonds would all be an average of the length of all those bonds experimentally. All right, so that's it for chapter 9. We didn't get to start chapter 10 today, but we'll talk a little bit about it for our class on Friday. Let's see, let me open up the syllabus here. Let's see. So Friday is our last class, and we were supposed to be talking about properties of gases, but it doesn't look like we're going to get there. We will talk a little bit about chapter 10, And then after that, we won't have class anymore. Friday will be our last class. But I'll be open to doing review sessions from the 11th to the, the final will probably be available the night of the 15th or maybe early afternoon. I'm not sure. They said they're going to get me the questions on the 15th. And then, but for sure, the 16th and 17th. And I don't know how late we can have it open till, but if it's open, if it can be open on the 20th, I'll go all the way to the 20th. But for sure, the 16th and the 17th. We'll see if I can go 18th, 19th, and 20th. Okay, but it'll be an online quiz, and you'll just get on just like you would normally do, but we're going to have something called Proctorio watching you. Yeah, I think that's it. Why don't we get a quick poll right down below in the chat if you have, say yes if you've worked with Proctorio, no if you haven't. Okay, so I haven't myself. Kylie, would you like to tell us whether you think we should have some sort of practice quiz where Proctorio is used so that it makes you feel better? Do you think that that'd be okay, or are you important? Or do you think it'll be a seamless process for those who haven't worked with Proctorio for the first time?
My stats teacher had a quiz open for people that wanted to.
Wanted to practice?
Try it out, and like she was the optional quiz, and I was fine with Proctorio, so I don't know. It could be an option.
You think it's a good idea? Anybody else?
Yeah, I think it's good for optional.
Okay. So I'll open a
But
practice.
it's pretty easy to use.
Okay. I'll open a practice quiz so that you can become familiar with how to get started with Proctorio so that doesn't become an issue. And other than that, are there any other questions?